This presentation is a significant wood design and construction changes to the 2018 IBC and NDS. The course number is BCD 121, and my name is Michelle Camberon. I'm the Senior Director of Education for American Wood Council, and then Lori will be joining us, and she is the Manager and Education Outreach person for AWC. So thank you, everyone. We have the copyrighted slide here for this presentation. Hopefully all of you have downloaded a PDF of the presentation, and if not, that information was provided for you in the chat box. And then this is a presentation that is registered with AIA as well as ICC and NCSEA for continuing education. And then we have the descriptions and then the learning objectives. So just high level, we'll look at the changes between the 2015 NDS and the 2018 NDS, which Lori will talk about, and I'll talk about the 2018 IBC and the changes from the 2015 IBC. We'll also touch on changes related to ASCE 716 and wind loads and how that affects wood construction. That possible increase in wind loads is what has triggered some of the major changes in the NDS. And then we'll look at some fastener changes related to address the increased wind loads, and then nail designs or fastener designs related to the increased demand on our wood structures. So our first poll, not counting the first one that we talked about, but we'll look at what is your profession? And Marcy, you want to come back and launch that?
I sure do. So as always, we like to know the field that you work in, just to get an idea of who's out there and what you're doing so that we can tailor our presentations to you. All right, 75% engineers, 17% code officials, 4% architects, 4% builder, manufacturer, or other. So no matter your profession, we are delighted that you're here and hope that you find something of value to take back to your workplace today.
Great, thank you, Marcy. And thank you for participating in the poll question. And as a reminder, these poll questions do not count towards your continuing education certificate. We base it on the time that you are in the webinar. Now, the first part we'll talk about is the IBC, and these are some of the significant changes that we're going to talk about related to exterior balconies, fire retardant treated wood, heavy timber and mass timber construction, and construction type. A little bit background for those that aren't familiar with American Wood Council. Some of you may know us as AFMPA, American Forest and Paper Association, but we are now currently American Wood Council and became that in 2010 formally. But our National Design Specifications for wood construction go back to 1944, where that was developed in conjunction with the USDA Forest Products Lab. And then through various iterations, incorporating new information about wood construction, changes in construction, we now are on the 2015 and then changing to the 2018 NDS. And in addition to the NDS, some of you, if you design for wind and seismic, you're familiar with this. We have the 2008 wind and seismic, or special design for wind and seismic provisions. Some people call it SPIDWIS, but we have the 2015 is the next edition out after the 2008. And you'll be happy to note that when we incorporate or the code references the 2008 NDS, it does adopt the 2015 wind and seismic provisions because we don't have a 2018. We are currently in the process of going through and looking at the changes for the 2021 wind and seismic changes. So look for that when the 2021 IBC comes out. Now, also like to point out is the American Wood Council is an ANSI accredited standards developer. So we do that through a consensus-based process through our Wood Design Standards Committee that looks at just major things related to fire protection and structural as other issues that may arise. And we have the incorporation into our standards. We have not only the NDS, but we have the wood frame construction manual, the permanent wood foundation standard, and the wind and seismic provisions. Now, just high level looking at when we get our new code, some of you, it may have been 3 years since there was a different code change, or maybe 6 years. Some people are going to a 6-year cycle. But just a review of the code changes. What we see is a vertical solid line in the margin, and that indicates a technical change that was from the 2015 IBC. And if there is a horizontal arrow that's shown here, that means there was a deletion in the section of the code. And then if we have a single asterisk, that means that in that section, a table of text has been relocated somewhere else in the code. And then a double asterisk means that in that section where the double asterisk occurs, that text or table has been relocated from another area into the code into the area where the double asterisks are. Now this lists all the relocations of tables that are shown here. And this is a 2005 column, and then we have the 2018 column. But note these chapter 23, that's a majority or more than half of what has changed from as far as relocating of tables. And that has to do with heavy timber construction, and we'll get into that in a little bit. So right off the bat, chapter 2, that's where we go to get our definitions, and very helpful chapter if we're wondering about what something means in the code. This is the first chapter you would want to go to for a term or a definition. And we see that there's a modification in the definition for conventional light frame construction and light frame construction. And what it the modification did is it used to say a method of construction whose primary structural elements, et cetera, et cetera. So a method of construction has been stricken out. And this is something that was did not get picked up in earlier printings, but it did get passed in the code changes. And there's an errata. So make sure you always want to be up to date and subscribe to the erratas that have occurred when a printing of a code has occurred. This has to do with fire retardant treated wood on the exterior walls. Now, when we are dealing with wood construction, it's primarily used in type 3, type 4, and type 5 construction. Although type 1 and type 2 construction does allow the use of wood. Well, in this chapter 6, that's where we go to get our definitions and what types of constructions are defined and what can be used in those types of constructions, or in chapter 6. In 602.3 and 602.4, having to do with type 3 and type 4 construction, it requires non-combustible exterior walls. However, it does allow fire retardant treated wood to be used as a non-combustible material. And so when there's a statement that says that fire retardant treated wood framing is permitted to be used in these exterior walls. Well, now the code says wood framing and sheathing. And that's because some were considering that only to be applied to the studs, that fire retardant treated wood is only applied to the studs, but it's applied to the sheathing as well, because we're talking about those exterior walls. Also, ASCE 7 considers sheathing as part of the wall framing. So now, just to make it more clear, not only the studs, but the sheathing may be of fire retardant treated wood. And So this in lieu of non-combustible to permit fire retardant treated wood, it is in walls that are of 2 hours or less. Another thing that you want to be aware of is in type 4 construction, it does require a minimum 6 inches thickness for that exterior wall. There was an effort to eliminate that 6 inches. It's not required in type 3 construction for a minimum 6 inches, and it may be that eliminates the need or does not allow 2x4 construction when we're looking at 6-inch dimension. But there's no real reason that could be found when looking at historical support for this, that 6 inches is not really a reasonable thing to, well, I shouldn't say reasonable. It's just something that is not applied to other types of construction, type 3 construction. So there was an effort to eliminate that requirement of 6 inches, and it did pass. But for whatever reason, when there was a correlation between when it went through the code process and the approval of the code changes and putting that into the printed document, it was missed. So there was an effort to put it in an errata or something, but certainly we'll see it when we get into the 2021 code. And you may look back at what was actually passed and use that to substantiate eliminating that minimum 6-inch difference or minimum thickness. Okay, when we're talking about type 4 construction is that type of construction that is heavy timber, and it requires minimum sizes to meet the requirements of heavy timber construction. So that's a coordination between the architect that categorizes their building as heavy timber and the engineer in specifying the right dimensions to meet the requirements of heavy timber construction. Now, those minimum requirements were in Chapter 6, and there was all kinds of information for the roof, the floors, the columns, minimum sizes. Well, now that information has been migrated to Chapter 23. So I highlighted this in the beginning of the presentation where some tables were moved. These are the tables that were moved to Chapter 23. One question that we get and have gotten in the past quite a bit is, what happens when we have a post or built up stud in a fire resistance assembly? Does it need to be encased? Some say, since it's a column, it does need to be encased. Well, in light frame construction, that's not really the case because our major structural system is based on a bearing wall system. We're not based on a post and beam type construction where there's not a lot of redundancy. It's a light frame system with bearing walls. So we've heard that some code officials were requiring these columns, even though they were in a fire resistance rating, to be individually wrapped. And that can cause some architectural issues because it could bump out that wall. So this comes from in Chapter 7, where they have the requirements for fire protection. And there's a section specifically to columns that states that the individual columns need to be encased. And what I'm talking about here is, say you have a type 3 construction, we have a primary structural framing requires 1 hour fire resistance rating. For type 5 construction or type 3 construction. And so there's clarifications now in Chapter 7 that says for light frame construction, studs, columns, and boundary elements that are integral elements of a wall between the top and bottom plates, or tracks, because this also applies to cold formed steel, may be permitted to have required fire resistance rating provided by the membrane protection of the wall. And so that clearly spells out that if you have, from our DCA 3, it's a 1 hour fire resistance rating, and it needs to be protected from both sides in this case, where we have a column that is in the wall. So no additional fire resistance is required for this, provided that this is a fire resisted assembly here. When we're dealing with, or the architect is dealing with expanding the footprint of the building, and within certain types of construction, an architect may introduce firewalls in a building so that when we're calculating our square footage of a building, say, by introducing firewalls in a building, we can almost double the size of our building. And what happens is these firewalls, we know, need to be structurally stable from the roof to the foundation so that in the event of a fire, if there's a fire on this side, this firewall protects it from expanding to the other side, because we're treating these two sides of that firewall as two separate buildings. So that's why it needs to be structurally stable, and there's a separation here. However, from a structural standpoint, if there's any kind of separation, we cannot treat those two buildings as one building. So they've got to be structurally analyzed separately and with this gap. Well, this can be an issue when we're dealing with lateral loads, because now we don't have a diaphragm that runs through to make it one continuous diaphragm. So, and especially in high seismic areas, where if we have two buildings together and they're treated as separate buildings, we've got to provide a seismic separation between those two buildings so that they don't hit each other in an earthquake. And so during the code change process, AWC was involved in introducing a code change to allow that diaphragm to go through. And so we tried to get it for high wind also areas, but what was passed is in seismic design categories D, E, and F, we now are allowed to have that diaphragm go continuous through the building or through those firewalls. And provided that it's in seismic design category D and EF, and the maximum thickness of the sheathing, floor or roof, is 3/4 inch. And so that became, is a result, or was started off back in 2006 when California started adopting the IBC and this requirement of having a separation between the buildings. Efforts by the SEI Light Frame Construction Committee developed this seismology opinion that states that looking at seismic issues and lateral loads on our building, it's very important to have that diaphragm go through. So that was one of the supporting documents to substantiate that code change. Okay, shifting now gears to deflections. When we look at our roofs and our floors and the deflection requirements, or our exterior walls, there are some deflection requirements shown here. These changes, or actually clarifications, has to do with a footnote that we're going to look at for floor members and roof members, and then also for when we're looking at wind designs, especially when we're looking at exterior walls or roof walls and the deflection criteria there. So first off, we'll look at footnote D, and when we're looking at wood members and the deflection criteria. Now the top footnote, footnote D, is from the 2015 IBC, whereas the bottom footnote is for the 2018 IBC. And you'll see that it used to state, when we're looking at deflection, it had for deflection limits for dead load plus live load. Well, that only includes live load for a threshold of 20 pounds per square, or less than 20 pounds per square foot for roof live load. Well, now this incorporates both dead and live load for regular live load, a floor live load, and extends it also to all roof live load to check for our deflection limits. And then also, there was a clarification when we're talking about long-term creep component for long-term deflection. So what it stated is for wood structural members in that are dry at time of installation and under dry conditions of use. Well, what does that mean by wood structural members? Well, to clarify that, it expands this and says for lumber, structural glue laminated timber, I-joist, and structural composite lumber that are installed, they're dry at time of installation and under dry conditions, the creep component for long-term deflection shall be permitted to be estimated at 0.5 times the dead load. And then where we have lumber, glue laminated timber that are installed, also cross-laminated timber that are dry at installation and the use in dry in the condition use, those parameters, then you use 0.5 or you use 1.5 times the dead load to estimate that creep component. And then for others that are beyond that I-joist, structural composite lumber, then the value of 0.5 will be used. And then for using this value of 0.5, then you don't use this when we're looking at the deflection criteria in the NDS for long-term loading. So these are separate, different things. When we're looking at the IBC, we use this criteria for estimating that creep component. And then the second aspect of deflection criteria has to do with what do we use when we're determining our wind loads for deflection criteria for wind resisting lateral loads out of plane. Well, in the 2015 IBC, we were able to determine our wind loads using 0.42 times our components and cladding loads. Now they've expanded that and allowed now, also in addition to that 0.42, we're now allowed to determine our wind loads using direct calculating using 10-year mean return interval wind speeds for determining. And this is just for deflection alone. Okay, when we're designing buildings, sometimes we'll have balconies or deck out here. This is an example where we have a balcony. What loads do we use when we're determining our structural capacity of our system? Well, as we know, when we're dealing with the IBC and ASCE 7, sometimes they are not in sync when they are being developed. This new change is actually updating the IBC to be the same as the criteria in ASCE 7. And that is, this live load out here is now 1.5 times the room live load, or a maximum of 100 pounds per square foot. So the threshold is 100 pounds per square foot. And previously, it used to say that use the same live load as occupancy served. Well, now we're in alignment because now it's 1.5 times the room live load. And although the IRC still has same as occupancy served. So this affects those buildings that are being designed under the IBC. Chapter 16 now has a section related to tsunami loads. This is for those that are in risk category 3 and 4 structures that are located in tsunami design zone areas. We have new sections and new definitions for those that are critical infrastructures and essential buildings. So some design criteria in Chapter 16. Here's some clarifications that are made related to structural observation and structural inspection. Now, structural observation may be required, and it's in section 1704.6. The first section, 16.1, is a general section on structural observation. Then we have 6.2, that's structural observation on seismic, and then wind, and then 6.3 covers seismic. So they've made some clarification in the language throughout that section that there was some differences between seismic and wind and general. And so in order to not be in conflict with one another, they've made some clarifications, and everything common to wind and seismic has been put into the general section and clarified the language. Now, there's also triggers that were occurring in the wind section, 6.2, that trigger whether or not structural observation is required. And so the wind has been updated to 110 miles per hour from 110 to 130. And that's just the change that we saw in the last code, where we went from an ASD design to an LRFD or strength design, and to be in line with that, now that's been updated to 130. Another thing related to special inspection has to do with when is special inspection required, and there's an exception to the rule on when it's not required. And this has to do with the wind main force resisting system. And what it stated is that special inspection is not required for shear walls, shear panels, etc., where the fastener spacing of the sheathing is more than 4 inches on center. So for those familiar with construction, we know that we specify boundary nail, edge nailing, and field nailing, and we could have fasteners at 4 inches on center, or nails at 4 inches on center at the edge nailing and boundary nailing, and then 12 inches on center for field nailing. Well, some could say that, well, okay, we have fasteners at 12 inches on center, then special inspection is not required. Well, that is not the intent of the code. It is the edge nailing or the panel edge nailing. So now that's been clarified, and what it states is where specified fastener spacing at the panel edges is more than 4 inches on center, then special inspection is not required. And so that is for the wind section, and for whatever reason, that was not picked up for the seismic. And so AWC has submitted a change for the 2021 code that was approved, but know that the intent is that special inspection is, the exception to that rule was meant for both wind and seismic. Okay, we have a poll now. Marcy, you want to come back and launch the poll?
I do indeed. So here we go. Which of the following is not true for floor sheathing at light frame double firewalls? It may be 1 inch thick, continuous through firewalls in seismic design category, sorry, E through F, continuous through firewalls in high wind zones and seismic design category D, or answers B and C. 32% say answers B and C, 56% say 1 inch thick, and just a few for the other two. So, Michelle, what do you say?
All right, so the answer is 1 inch. And the tricky part is which is not to. There's another tricky part, but let me go back to this. So yes, this is not true, 1 inch, because you're only allowed 3/4 inch. There's another tricky one in here. But for this, continuous through firewalls, this is correct. It's seismic design category D, E, and F. And then continuous through firewalls in high wind zones and seismic design category D. And that's correct because it's in seismic design category D, so we are allowed to have those sheathing, floor sheathing pass through. And so the incorrect answer is 1 inch. Okay, thank you for participating. Now into chapter 23, the wood chapter. And we would see that our reference standards have now been updated. And you'll want to update your notes and specifications. We have the 2018 NDS. And as I mentioned previously, we still have the 2015 Special Design Provisions for Wind and Seismic. And then we also have updated the 2000 NDS Wood Frame Construction Manual. And we have also the ASCE 117-2015 specifications for structural glue laminated timber and softwood species. So all of these related to design of wood construction. Now our manufacturing standards for manufacturing performance rated engineered wood siding, cross-laminated timber, structural glue laminated timber, and engineered wood rim board. So all of these have been updated. One thing to point out is, yes, we have cross-laminated timber, and cross-laminated timber actually was first adopted into the code in the 2015 IBC. And also we have the siding, wood siding. Now remember, siding, for those of you using wood siding, it can also be used as a shear wall. And so very important to make sure our standards are up to date and referenced up to date. And then the engineered wood rim boards. These are very important because not only do they act for gravity loads and continue our load path down the building, but also in plane lateral loads for continuing that load path. Now, fire retardant treated wood, I mentioned, and it can be used as a substitute for non-combustible materials in Type 3 and Type 4 construction at that exterior wall. And there are specific requirements when we're talking about what does it mean to be fire retardant treated wood. In Chapter 23, we would see, and this helps just to go to the code language, 2302, fire retardant treated wood. And fire retardant treated wood is any wood product that when impregnated with chemicals by a pressure process or other means during manufacture. And this is where there were some question about what does that mean by other means? And what does it mean to be fire retardant treated wood under this definition? So the other means here during manufacture, now it specifically states that when the products are impregnated with chemicals to provide that non-combustible, to be categorized as non-combustible or substitute for non-combustible construction, it's got to be impregnated. And also, the use of paints, coatings, stains, and other surface treatments are not an approved method of protection as required in this section. Now, we know that there are other products out there that do provide this treatment, the topical treatment, basically. And in order for those to be provided as a non-combustible material, then they would need to go through the alternate means approach, which is 104.7, I believe, is the section. And then the code official will more than likely request a ER report or some testing to substantiate that it can be substituted for under this definition of a fire retardant treated wood. And there are products out there with an ER report. Now we're looking at mechanically laminated decking, also known in the industry as nail laminated timber. And it's actually been around for quite some time. I did a Google search of past codes. Some of you probably familiar with the UBC. And even back as far as the 1967 UBC, it had mechanically laminated timber or decking. And almost similar, pretty close to the language that we have for the prescriptive requirements of how these members are connected together. Now, it doesn't specify a type of nail like 10 penny or 20 penny nail, but what it does say is a minimum diameter of a nail, and the length of the fastener needs to be 2.5 times the lamination. So if we're talking about 2x members, 2.5 times a lamination would be 3 3/4 inch length of nail. So in order to meet that length of nail, you would pretty much have to use a 20 penny nail, which is a pretty good size nail. Well, now, this shows you a picture of the actual nail laminated timber. This is a building actually in California. The structural engineer was Structural Focus. And this shows you an animation. We have 2x. This doesn't show the actual fasteners that connect all them together, but shows you what it actually is. And there's a certain spacing of those fasteners and a staggering of those fasteners up and down the member to connect it. And as I mentioned, minimum length of fastener. So we have a new table now to make it more applicable to what we're seeing in the industry with how nails are driven and using pneumatic nail guns. And so we have fastener schedule for mechanically laminated decking for 2x nominal thickness of members that also provide the diameter and the minimum length of nails, as well as the spacing of nails, staggering them, and also the toe nailing into the support. So now that they not only have the prescriptive requirements of that 2 times the length of the nails, now we can use nail guns and use this type of nailing schedule. We've also updated our tables. This has to do with demand now on the buildings to meet those high wind demands on the building, and introduction of 8 penny and roof sheathing ring shank nails. And these tables are in chapter 23. There are nailing schedule or fastener scale schedule. And what we found is that when testing was done on, say, the 8 penny box nail, it showed that there was insufficient capacity in that 8 penny box nail in lower density roof sheathing when we're in the high wind regions. For example, when we're in 130 or 140 mile per hour areas, that the 8 penny or box nail just didn't provide that capacity. So now we've changed that to an 8 penny common nail and also included a roof sheathing ring shank nail. And Lori will get into this more later on in her presentation about this roof sheathing ring shank nail. Now, this was previously incorporated in the IRC. It's just now incorporated in the IBC. The heavy timber construction, type 4 construction, as I mentioned, was in chapter 6, and now it's been migrated to chapter 23. We see a new table here in chapter 23. Previously, there was only the sizes when it was in chapter 6, and now we have more information to make the table more user-friendly, where we have the supporting, what's roof loads that it's supporting or floor loads, and then the element that we're talking about. And note that we have nominal sizes for solid sawn lumber, and then we have the actual sizes for glue laminated timber and structural composite lumber. And then this section related to balconies. So we know that wood structures throughout the nation have been used successfully without any issue in the balcony areas or the decks that are exposed or walking decks. But there are some areas that have been having some challenges related to when moisture has intruded into the wood structure. And so to mitigate against possible issues in the future, the code has been updated to provide some measures in place. One of those has to do with Chapter 1 of the IBC and the IEBC, the existing building code, that now requires details in the construction documents and inspections for the impervious moisture barriers on those exterior balcony areas. So very important, details and inspections where we have these impervious moisture barriers. And just a picture of what we see is we have a permeable floor area, a moisture barrier here. We want to have positive drainage at this exterior area. And this shows for a wood joist through. So what it's requiring now, where we have impervious moisture barrier systems, and then it's protected by a permeable floor, it's requiring that positive draining is required. That makes sense. We want to drain away from this area so that it doesn't drain into the interior of the building. But also, what's not noted here is that in this area where the wood is, we want to have ventilation provided. So in the event, if there is some water that infiltrates, then there's ventilation that allows or provides some ventilation in this area that allows the wood to dry out. Okay, now we're into the conventional frame construction, that chapter 2308, where we've now expanded the use of wood products so that not only Southern Pine number 1 is included in this table, but we've expanded it to Southern Pine number 2. And so now, because Southern Pine number 2 is a lesser grade than number 1, you'll see that the length of the members that are allowed, the span length, is going to be decreased a little bit, just so it opens up the use of other wood products that are readily available in the industry. So this is for both exterior bearing walls and as well as for the interior bearing walls. We've also updated the tables, and I'll go back to this, related to when we're looking at headers. Sometimes we have headers that are flushed and they're braced out of plane by the floor system. And we also have an installation where the header could be dropped, and we only have a cripple stud above that. So it's not braced out of plane. So to accommodate into the header tables or girder tables, we now have something that accommodates for that when we have dropped headers. And so here, if the span is dropped, then for 2x8 and 2x4 and 2x12, 2x8, 2x10, 2x12s, then the lengths need to be reduced by 20% or 30%. The spans that are calculated need to be reduced by 30%. And that's reflected here in the footnotes. Another measure that we've incorporated in is, because now we want to be more energy efficient in our buildings, we are going to allow now a 1x header or 1 header or a 2x header in the envelope exterior walls. That's limited to 2 to 4 feet, and this allows for insulation to be allowed in that cavity where the header is to provide a more thermal performing building. Now, the last part of this is having to do with ASCE 716 and the changes that have occurred related to wood construction. So what we see is ASCE 716. General references are in chapter 35. And while this was being developed, we see that it references, we have some wind designs and seismic designs that have been updated in ASCE 716. That is consistent with what is in the IBC. And then there's references also for specific seismic provisions are coordinated within the IBC and Chapter 18 and related to ASCE 716. So the references are the same. And then when we determine our snow loads, there are 3 paths for determining our snow loads. And this is where when we design our building, we want to coordinate with the authority having jurisdiction, our building department, or other authority having jurisdiction, and make sure that we're on the right path for determining our snow loads, because there are 3 paths. One is using the criteria in the IBC to determine our snow loads. There are figures in 1608.2 and tables for Alaska, but that's one path for determining the snow loads. There's also tables within ASCE 7 that for determining snow loads. And then you could also have state maps or even local maps. So we want to make sure that we're using the right tables or paths for determining our snow loads. Now, there was an effort to have one path and have it all consistent, but that unfortunately did not pass. So another reason to get involved with a code change process, as design professionals and code officials, to provide some consistencies. Okay, another effort or another thing to be aware of has to do with roof drain and related to rain loads. As engineers, you're wondering, why do we have to know about roof drains? Well, we need to determine or be involved when we're dealing with our design of our roof structure and possible ponding that can occur, and coordinating with the architect, because the architect may not know that this is in ASCE 716. So a secondary drain may be required, and there's 2 criteria for determining whether or not a secondary drain is required and what that criteria is. In ASCE 716, for that secondary drain, it's based on a 15-minute and 100-year event. In the IBC, it's based on, for both the primary and secondary, a 1-hour and 100-year event. So we want to make sure we're in line with the code official. We want to make sure we're in line with the architect to make sure that we have some agreement on what the criteria is for that secondary roof drain. Now, we've had some changes related to wind loads, and the wind loads have changed. It's based on, in ASCE 716, over 1,000 weather recording stations across the country. So we have more information, more detailed maps, and how it affects what's in the NDS is what Lori is going to go over, but our wind speeds have changed across the country. This is a representation of the basic wind speed for risk design category 2. And you can see we have some interesting contours across the map. And then this is what was in the previous ASCE 716 for risk category 2 for basic wind speeds. So more information from the 100 or 1,000 weather recording areas. So in some area of the country, your wind speeds may decrease or it may increase depending on where you're at in the country. And that may increase your demand on the building. So if you're interested, this is a really helpful article by Don Scott that gets into more detail on the changes in ASCE 716. NCSEA also has a recorded webinar that he's done for him, so more resources to find out. So when we look at the dealing with our wind demand on a roof. We've got uplift on the roof that we've got to design for. We have different zones on our roof. So we have here we have R3, 2R, et cetera, et cetera. And then there also is an overhang area that we design for. And we use our components and cladding loads to design that area. If we look at a comparison between those components and cladding roof coefficients, we would see here in this table a ratio of ASCE 716 versus ASCE 710. And so anything over 1 is going to be an increase when we're looking at our roof coefficients. This is looking at the roof overhang, and this is just looking at the rest of the roof. And looking at those R3, 3R areas, 3E areas, et cetera, et cetera. So anything over 1 is going to be increased. And so you will see that in these areas, most of it are going to have an increase in that components and cladding and the roof coefficients. And a lot of them are going to be over 1.5. So we're going to have, even over here, when we're looking at the slope here, and I should have mentioned that previously, this is the slope of the roof, we have almost 2.5 times increase in the 3E region. And so that could cause an increase in your demand on your roof. And I say could because when we look at our wind pressure or maximum pressure that we've designed for, it also includes the wind speed. So in areas where your wind speed has decreased, that decrease could offset this increase in our when we're looking at our coefficients, our external coefficient, wind pressures, and when we're looking at those different zones. But definitely something we certainly need to look at. Now for resources in the changes, we have this article that's been published in Structure Magazine on the 2018 IBC and the 2018 IEBC. And we have also, in addition to a commentary, we also include an Appendix A that shows the actual language that was changed. So helpful to look at. And then there's an article referenced here when we're looking at more information related to those balcony areas. And architects, those engineers in the audience may want to provide this to the architects. It has a lot of information related to detailing requirements. So we have one poll that we're going to do. And Marcy, you want to come back and look at this poll? And then I think we're going to go directly to Lori after this.
Okay. So exterior balconies with impervious moisture barrier system over the wood structure supporting moisture permeable floors shall have is that A, positive draining of water, B, ventilation below the floor system, C, details in construction documents, D, inspections for impervious moisture barriers, or E, all of the above. 94% say all of the above.
Woohoo!
What do you say, Michelle?
Okay, and the answer is all of the above. Let me give the animation. So all of the above, exterior balconies, and this is those balconies with impervious moisture barrier systems over wood structures supporting those moisture permeable floors. Positive drainage. Yes, we don't want the water to run back into the building. We want it, and we don't want it ponding up on that balcony. Ventilation below the floor system, very important, so that if moisture does penetrate, we want to be able to have that air out. And details in construction documents, yes. And that was in chapter 1, as well as inspection of that impervious moisture barriers. So now I'm going to hand it off to Lori, and she's going to come in. If you're ready, Lori, I know we talked about having some questions, but let's go ahead and
I am ready. Yeah.
All right.
All right, you should be seeing my screen there. Thanks, Michelle. Thanks, Marcy. So as was mentioned, I'm going to spend the second half of the webinar talking about the 2018 NDS changes and the updates that have been made to the document in this latest edition. As you know, the 2018 NDS is referenced in the 2018 IBC. Michelle mentioned that. It's also in the IRC, or the Residential Code. Additionally, the latest document for shear wall and diaphragm design is our special design provisions for wind and seismic, or you might hear it referred to as SPIDWIZ. There isn't a 2018 update of this, so the 2015 edition is still the latest and greatest, and that is also referenced in the 2018 IBC and IRC. So the primary changes in the 2018 NDS are listed here. The biggest one, as Michelle mentioned, is probably the reference of ASCE 716, updating that reference from ASCE 710 as it was in the previous version of the NDS. We also, kind of tying in with that, added some new provisions and some updates for different types of fasteners. So we added an equation for withdrawal of smooth shank stainless steel nails. We added some new provisions for roof sheathing ring shank nails that have been adopted into the ASTM F1667 standard. There's also some new provisions related to fastener head pull-through. That's a new limit state that you have to calculate. We've revised some lateral design, revised the calculation for lateral design values for deformed shank or for threaded nails, as well as some revisions for timber rivet design values, the tables therein. In Chapter 16, the fire design of wood members chapter, there was some revised terminology. The changes in Chapter 16 were not technical in nature, they're more editorial and meant to make things a little bit more clear. There were also some changes in the NDS supplement that included removing redwood grades requiring close grain. Norway spruce from Norway was also added to the foreign species dimension lumber table, and then the addition of shear-free moduli of elasticity for softwood glulam or glued laminated timber. The overall format of the NDS is the same as it was in 2015. So the first 3 chapters are our general topics chapters. Chapters 4 through 10 are our product chapters. And then chapters 11 through 14 are connections. And then the last 2 are specific topic chapters. So you can see the way it's organized, and the red asterisk next to the chapter title indicates that we made some changes in the 2018 NDS that chapter. So again, the appendices that are included in the NDS, there were only some revisions to Appendix L, and that's related to the addition of these new roof sheathing ring shank nails. So there weren't any other changes to the appendices. As I mentioned, there were also some changes in the NDS supplement, which is a separate book from the main body of the NDS. So this has been updated just to provide the latest design values for solid sawn lumber, for glulam, and the other products that are included in there. So from here on out, I'll just go through chapter by chapter and go through the changes in each chapter. So we'll start at the beginning in chapter 1. As I mentioned, the update to ASCE 716 has been one of the biggest changes in this standard, and some of the changes that kind of followed kind of cascaded from this due to the, as Michelle talked about, these increased component and cladding loads. So the update to ASCE 716 is kind of tied into the addition of these new roof sheathing ring shank fasteners. Also in Chapter 1 is the notation, so all of our variables and things like that. So some notations have been updated to reflect changes due to clarification of calculating deflection for CLT. So you can see the first handful there related to that. The EI sub EFF and GA sub EFF use the effective bending stiffness and the effective shear stiffness in the calculation for the apparent bending stiffness of a CLT panel. The W sub H and W sub H prime are the reference and the adjusted fastener head pull-through design value. And the T sub NS variable is related to that equation, the equation used to calculate those values. For the fire chapter, you see this changes with the A sub char and then the beta sub T. So again, these are just some clarifications. In Chapter 2, we had a change in Table 232. This was a revision in footnote 2. So this relates to our load duration factors, which is the C sub D factor that's used in allowable stress design. So this is clarifying that the impact load duration factor of 2.0 does not apply to wood structural panel, and this reflects the current wood structural panel industry recommendations. So if you have an impact load in a wood structural panel, you would be limited to a load duration factor of 1.6. So regardless of what that load, if the load duration factor would be above 1.6 for a wood structural panel, you're going to be limited to 1.6 only. So with that in mind, we're going to jump into our next poll, which Marcy's going to launch for us.
Yes, she is. Give me 1 second. I apologize for that. All right, load duration factor C sub D for impact loads is limited to 1.6 for wood structural panels. Is that true or false? And 82% say true, 18% say false. And what do you say, Lori?
It is true. So that's that revision to this footnote of Table 232. So load duration factor for wood structural panels is limited to 1.6. So good for those of you who got it correct. All right. Here we go. Chapter 3 now. So Chapter 3 is the last of kind of the general front matter, if you want to call it that, the general provisions. There was a kind of a small looking but not unimportant change in the calculation of F sub B star in section 3.3.3.8, which is your beam stability factor calculation, or C sub L. So this is clarifying that the volume factor, C sub V, should be included in the calculation of F sub B star when C sub V is greater than 1.0. And that can be something that occurs in the case of structural composite lumber. If you're in section 8.3.6, which we'll look at, we'll look at the structural composite lumber chapter a little later. But if you have a C sub V greater than 1.0, then it would be included in the calculation of F sub B star. However, if it's less than 1.0, we would not use that. All right, so now we're getting into our product chapters, the first of which is Chapter 4, which is our solid sawn lumber chapter. And the first clarification that we see here is in section 4.3.7, and this is the flat use factor C sub FU. There was a new section added, section 4.3.7.2, to clarify that the application of the flat use factor, the C sub FU factor, in adjustment table 4.3.1 is required for beams and stringers as well as dimension lumber. So it's not limited to just, your nominal 2x or nominal 4x. It would be applied to larger material as well. The next change that we see here in chapter 4 is in 4.3.8, which is the incising factor section for C sub I. Now, incising is done on lumber that's being treated, and it's only done for what we call the refractory species. So that includes Douglas fir, spruce pine fir, and hem fir. So it does not include southern yellow pine. So these refractory species need to be incised to allow treatment chemicals to penetrate the wood. So when you do incise the lumber, it does require the application of an incising factor. And typically, those incising factors had been taken from table 4.3.8. However, you're now permitted to use a different incising factor for your incising pattern and for your lumber size when it's obtained from the company providing the incising, or the manufacturer, whoever. So this is an alternative to the approach that's in table 4.3.8. So you can still use these values, but if you have different values from the supplier, then you can use those values. Chapter 8 is our structural composite lumber chapter. So when we say structural composite lumber, or SCL, that includes things like laminated veneer lumber, laminated strand lumber, oriented strand lumber, and parallel strand lumber. And for those of you who may have missed it, LSL, or laminated strand lumber, and OSL, they were added to this chapter in 2015. A change was made to clarify that the dry service conditions that are associated with conditions in which the moisture content of sawn lumber is less than 16% is in line with what would qualify as dry service for structural composite lumber as well. So this is for end use in dry service conditions, so like when you have protected framing members inside of an enclosed structure. So the average equilibrium moisture content for solid sawn lumber in most of these is considered less than 16%, and then the conditioning environment of that is considered representative that it would also condition structural composite lumber to less than 16% moisture. So just kind of clarifying that. There was another change made that it appears in table 8.3.1. It's the inclusion of a volume factor for structural composite lumber tension parallel to grain values. So that's the F sub T calculation. Chapter 8 was revised to include this volume factor for tension, and this is based on a correlating change in ASTM D5456, which is the standard specification for evaluation of structural composite lumber products. So this standard requires that you have a volume factor for tension. And another change that was made in this table that you can see is the footnotes for C sub L and C sub V were moved from the column heading up here down to the actual factor next to the adjustment factor. So it gives it a little more clarity. The next chapter is chapter 5. That's our glue laminated timber chapter that we're going to talk about. So the only change we really see in table 5.3.1 is, and again, this is our adjustment factor table for glue laminated timber, is that we added a footnote to clarify that the adjustment factors C sub M, which is your moisture factor or your wet service factor, and C sub T, which is your temperature factor, they shall apply for shear parallel to grain and should be used to adjust the reference radial tension, which is the F sub RT value. This clarification was added because in table 233, where we talk about temperature factor, and in section 533, where we talk about the moisture factor, they don't specifically reference this F sub RT. So this footnote and this clarification picks up that you do apply them to this value, those two adjustment factors to this value, even though it's not specifically mentioned in the main body of the text there. All right, chapter 10 is the cross-laminated timber chapter. This is the newest chapter in the NDS. It was just added in 2015. And we've made some adjustments in table 10.3.1 that you can see here. The primary adjustment, or the primary revision that we see in this table, is revising the format conversion factor, or the K sub F factor, for rolling shear. And it was adjusted from 2.88 down to 2.00. This is another one of those changes that comes from an ASTM standard. So there was a change in ASTM D54, 57, and this format conversion factor of 2.00 is consistent with what's in that ASTM standard, and it's also consistent with the assumptions implemented for modulus elasticity and for compression perpendicular to grain design properties, which aren't adjusted for either the load duration or the time effect factors. There were also revisions made to the CLT deflection provisions to include this term GA sub EFF, which is the effective shear stiffness of the CLT section. And this is a correlating change with the APA PRG 320 2017 standard that Michelle talked about. So PRG 320 is the production standard for cross-laminated timber. The NDS does reference the 2017 version of that standard, but again, most producers have upgraded to the, or gone to the 2018 version. So just be aware that there might be slight differences between what you're looking at if you're looking at different versions of the standard. But so this is a change that is correlating with PRG 320, and this is again just to facilitate the calculation of the apparent bending stiffness, which is what that EI sub APP value is equal to. Now the next group of chapters are the fastenings chapters, or the connections chapters. So chapter 11 is the mechanical connections chapter. So this is the kind of overall connections chapter. And then in chapters 12, 13, and 14, we talk about the different specific types of fasteners. And we're going to talk about chapter 12 in quite a bit of depth, because there were some substantial changes in there. And that's related to dowel connections. But again, we do also have provisions for split ring and shear plate connectors, as well as timber rivets. And chapter 11 would apply to all connections, all mechanical connections, regardless of what type of fastening they are. And the changes in the NDS connection design provisions were primarily in response to these significant increases in the components and cladding wind pressures in ASCE 716. So these wind uplift and these related changes, they're kind of what spawned some of these new fastener withdrawal and the fastener head pull-through design provisions. So the first thing you'll notice when you go into table 11.3.1, which is our adjustment factors for connections table, our kind of summary table, is that there's a new limit state, and we've talked about this previously a little bit, and it's this fasteners with round head or fastener head pull through. So you'll see it's denoted as W sub H or W sub H prime, depending on if it's an adjusted or a reference value. You'll also see in table 11.3.3 the addition of pull-through loads in the wet service or factor, or the C sub M factor for connections. There was the other revisions in the table. There was a reference to threaded hardened nails that was removed, and a new footnote was added for nails and spikes subjected to withdrawal loads, indicating that for a roof sheathing ring shank nail and a post frame ring shank nail, the appropriate C sub M factor would be equal to 1.0. Now, chapter 12 is one of those specific fastening chapters, and this one deals with dowel type fasteners. So that's things like bolts, screws, nails, and the other ones you see listed there. Now, one of the important things, and I briefly mentioned ASTM F1667 previously, but this is the referenced standard for nails in the NDS. So the provisions in the NDS will apply to other fasteners, and there is language in the NDS that says you can use other fasteners besides what is in the NDS. You just have to provide design values from the manufacturer, an evaluation service report, something like that. But in the NDS, and what's tabulated in the NDS in our design tables, we deal with only F1667 nails. And those nails have what is called a full round head, which you can see here in the picture on the left. If you have another type of nail head, and there's a few different types, I'm sure you could find, dozens of different shaped heads if you looked really hard. But the different shaped heads you'd need to find either in an evaluation service report, or in you'd need the manufacturer to provide some sort of acceptable literature that shows these design values. And one such evaluation service report that you may want to familiarize yourself with is ESR 1539, and that's the one that has been provided by the International Staple and Nail Tool Association, or ISANTA. So if you go into the ESR 1539, you'll see tables that look pretty similar to the tables that you see in the NDS and in the special design provisions for wind and seismic, and they provide design values in a format that's very easy to understand if you're familiar with the NDS provisions. So you can use other fasteners besides ASTM F1667, but we primarily, when we're talking about nails in this standard, and what I'm talking about today, I'm dealing with standardized F1667 nails. So with different types of nail shanks being included in the NDS as well, it's important to understand what actually is included in the standard and what is not. So the only types of shanks that are included in ASTM F1667 are smooth shank fasteners or ring shank fasteners. And the other types of nail shanks you might see out there, such as like a screw shank, or sometimes that's known as the twist shank, or the barbed shank, those would be outside of the NDS provisions, so you'd need to get design information for those somewhere else. But an important thing that you may want to note is when you're looking at a ring shank nail, you have the ring shanks, their nails are created by machinery and tooling. They deform a smooth shank nail that is made from pulling a round wire. And so you'd start with a smooth shank nail, you deform that shank by compressing part of the nail and rolling it. And this forms this root diameter, which you can see expressed. So that's kind of the narrowest part of the nail. The kind of outer part of that would be known as the crest diameter. And then you also have your undeformed shank diameter. So depending on where you are in the nail, there's 3 different diameters that could be present. So you do want to be aware that these numbers are different, but we'll talk about using the nail diameters in some of these equations in a little bit. In terms of nail points, NDS does assume that your nail is going to have a tapered tip, so that'd be either like the diamond tip or the needle tip. There are some nails out there that have a flat or a blunt tip, but the ASTM, or I'm sorry, the NDS assumption is that the nail tip length is equal to 2 times the diameter. And that nail tip length becomes important when you're doing your lateral yield calculations. You assume that you use 1/2 of that tapered tip length in your length calculation. So as I mentioned, the addition of roof sheathing ring shank nails in F1667 allowed us to add some additional language in our standard. So the roof sheathing ring shank nails are included in section 12.1.6 now, and a new appendix table L6. There is some clarification that in this standard that they do have to be the ASTM standardized nails, and they need to meet the requirements for the nail yield strength. There was also some additional language added about head diameters because that's required for the new head pull-through division or design provisions. There was also some language about threaded hardened nails in section 12.1.6.2. That was removed and replaced with a new provision for other deformed shank nails, and that's in a new section 12.2.3.2 D, that we're going to take a look at as well. So the 2018 NDS is the first edition of the NDS that specifically calls out smooth shank stainless steel nails. So there's been an update that has been added to distinguish between the bright or galvanized carbon steel nail withdrawal capacity and a stainless steel nail or spike capacity. So you'll see the withdrawal capacity equations at the bottom of the slide here, with the smooth shank nail being on the left and the stainless steel nail being on the right. And there's also new tables that were added or adjusted. So this one was actually just modified a little bit to reflect that there is a bright or galvanized carbon steel nail, and that's what this table corresponds with. So all this is really is expressing the results of that equation we looked at previously in tabulated form. So this gives you the withdrawal capacity in pounds per inch of fastener penetration into your wood member. This table 12.2D, is entirely new, and this is for stainless steel nails, the withdrawal of stainless steel smooth shank fasteners. And for those of you that are comparing the numbers, you might notice that the stainless steel values are, in some cases, substantially lower than the carbon steel nail values. And the reason behind this is because research had shown that, especially at higher specific gravities, that the withdrawal capacity of a stainless steel fastener was substantially lower. So you can see that reflected in the graphs here. So at a lower specific gravity wood member, like down here at 0.35, difference in withdrawal capacity for an 8D common smooth shank nail is not very much. But when you get up here into 0.55, so that's like a southern yellow pine wood specific gravity, there's a substantial difference, 15 pounds per inch or more in the withdrawal capacity. So there's been a demonstrated need to reflect that the stainless steel fasteners do have a lower withdrawal capacity than the carbon steel. Roof sheathing ring shank nails have higher withdrawal design values than smooth shank nails. That's why we use them. But they also provide, beyond that obvious increase in withdrawal or in holding power, if you will, they provide options for kind of cleaning up your nailing schedules. So we'll take a look at some different nailing schedules in a little bit, but using a roof sheathing ring shank nail can help either have a consistent nailing schedule across an entire roof structure, or have less tightly spaced fasteners. So there's definitely benefits to using these fasteners, and that's why we added them into the NDS. And you'll see that sorry, let me jump back here real quick. So you'll see that they do have their own withdrawal equation 12.2-5 here. That's for, again, only the ASTM standard nails. But if they meet that ASTM standard, you can use this withdrawal equation, which gives us, again, some greatly increased withdrawal resistance over a smooth shank fastener. So table 12.2E has been modified to accommodate these new fasteners that have been added, and you can see there are some new tables or new columns added for our various fastener diameters. Fastener head pull-through, I mentioned, is a new limit state that we now need to check for, and this is used to set industry recommendations for wood, or this has been used based on industry recommendations for wood structural panels. There was a great deal of historical data that was pulled from tests of lumber and plywood and OSB, and through a lot of painstaking analysis, they developed these new fastener head pull-through provisions. So within the range of head diameters and thicknesses and specific gravities in the NDS, the analysis found out that head pull-through is related to the perimeter of the fastener head. And these equations are based on the fastener head. The diameter is what you use, but that pi in there, remember back to geometry class, pi times diameter. So that's that perimeter of the fastener head, or the fastener head diameter. The specific gravity of the lumber, or of the material, whatever your side member is, it might not necessarily be the lumber, but so the specific gravity of the side member, and then the net side member thickness. So these are all of the variables that these equations for head pull-through are based on. So the T sub NS value, that side thickness or net side thickness. Now, the reason we say net side thickness and not just the thickness of the side member is, in some cases, depending on the type of fastener, you may bore out a little bit of that side member, and kind of countersink your fastener, so that the head of the fastener is flush and doesn't stick out. So that's all we mean by that T sub NS. If you've got a difference in your side member thickness, or for some reason, like that would be picked up by that. But again, it's the fastener, per the head diameter of the fastener, specific gravity of the member, and then the net side member thickness are the kind of three important variables in head pull through. And as we saw with the other sorry, I had to clear my throat there. As we saw with our other limit states, we do have a tabulated solution to our equation. So we added a new table here, table 12.2F, that reflects the fastener head pull-through capacities. So we're going to do just a quick example here and demonstrate the analysis that you'd need to kind of undertake when determining a fastener uplift capacity. So the uplift capacity of a fastener is going to be the lesser of the withdrawal capacity and the fastener head pull-through capacity. So the apostrophe or the prime indicates that these are adjusted design values. The example we're going to run through today, we're not going to look at every single adjustment factor, so we're only going to compare the unadjusted values, but I think we'll still get the idea of things. So this is our assembly. You can see that we have a 2x6 Douglas fir larch main member, and our side member is a 7/16 thick piece of OSB. Our fastener is called a dash number 5, and that's just what it's referred to. I know it's a little different than the 10-penny and 8-penny that we're used to, but if you think about 10-penny nails for a name, it's a little strange as well, I guess. The dimensions of the fastener are listed in NDS table L6. One thing that I do want to point out to folks is this TL value, or thread length, equal to 1.5 inch. So the actual length of the nail is 3 inches, but the deformed shank length, or the threaded length, is 1.5. So here's the rest of the equation, or of the inputs for our equation. I ran this calculation in MathCAD, so some of the more astute of you might notice the little colon next to the equal sign. That's just MathCAD formatting. But if we, again, these all come from Appendix Table L6, with the exception of our net side member thickness. That's our 7/16 OSB. Our G is equal to 0.5 for both of our members, but really we're only interested in the side member specific gravity for this example, which is the Douglas fir larch 2x6. Checking the fastener withdrawal, we'll use NDS equation 12.2-5, or we could use NDS table 12.2E. They give us the same answer, so it's 59 pounds per inch of resistance. And that's based, again, on the inches of threaded fastener shank length. So for us, that's 1.5 inches. So 59 pounds per inch times 1.5 inches gives us a resistance, a withdrawal resistance of 88 pounds. Checking our fastener head pull-through limit state, we see that our 2.5 times the fastener head diameter is greater than our net, our T sub NS, our net section, or net thickness of our side member. So we're going to use NDS equation 12.2-6A. Again, this is one of those, you can check it against the table or just pull it out of the table, but they're going to give you the same answer. It's the same regardless if you use the table or the equation, but it gives you a value of 67 pounds of head pull-through capacity. So our fastener head pull-through is 67 pounds. That's less than the withdrawal capacity of 88 pounds. So that controls the design capacity. And you'd go into NDS table 1131 for your additional adjustment factors based on your end use conditions. So that's things like load duration factor, your temperature factor, moisture factor, and things like that. If you jump into the wood frame construction manual, just in table 310, there's a little footnote table, if you will, that shows the different fastener uplift capacities for 8D common 10D box nails and then a roof sheathing ring shank nail -03. And if you compare these fastener uplift capacities, you'll see that with the framing member specific gravity of 0.42 or 0.49 notwithstanding, we can get some pretty high uplift capacities, especially when we start seeing these pretty thick side members out of our roof sheathing ring shank nails. So the possibility for kind of simplifying our nailing schedule exists when we're using these kind of higher capacity fasteners on our roof. So for a lower wind speed zone, like a 110 mile per hour exposure B, and even with a lower specific gravity framing, like a 0.42 specific gravity, so that'd be like a spruce pine fir. If we just use an 8D common nail, in our perimeter nailing zones, we'd need to have the framing at 6 inches on center at the edge and 6 inches on center in the field. So that's what this 6-6 indicates. So that is at the panel edge as well as the interior supports on the panel. And then when you get into the interior nailing zone, a zone 1, you can go to the 6 and 12 nailing pattern. If you use a roof sheathing ring shank nail in this same assembly, you would be able to apply a 6 and 12 nailing schedule for the entire roof. So that makes your construction a lot easier. It makes things a lot easier on the site when you can just keep it consistent. So that does give you different options when you're doing a design in a low wind speed area. What about a high wind speed area? So if you're in 180 mile per hour exposure B, and let's look at a higher specific gravity framing this time. So this is a G of 0.55, so that'd be for a southern yellow pine. And if we have like a complex roof where separating your perimeter and your interior zones is difficult, so something kind of like what we see in the picture here, it can make it a little confusing. So if we look at an 8D common nail in this type of setup, our perimeter nailing is going to be 4 inches on center at the edge and 4 inches on center in the fields of the panel in the interior supports. And then in those interior zones, it would be 6 and 6. If you go to a roof sheathing ring shank nail, you can have those nails not quite as tightly spaced together. So our perimeter nailing would be 6 inches at the edge and 6 inches in the field. And then our interior zone nailing is 6 inches and at the edge and 12 inches in the field. Oh, sorry about that. All right, another change that was made in ASTM standard was in ASTM F1575. This is the test method for determining bending yield moment of nails. So this clarified that the nail bending yield strength is based on the nominal diameter, which is D, and not the root diameter, which is D sub R. So this allowed for the simplification of the calculation of the nail moment resistance in the NDS yield equations. Because D is always provided for the nail types, D sub R is not always provided for deformed shank nails. So this made things a little bit easier in terms of calculating your capacities. Tables 12Q and 12R, which are our capacity tables that are listed in the NDS, were revised. And you can see that they added roof sheathing ring shank nails as one of our fastener options. So you can see the column here that was added. All right, we got one more poll. I'm going to have Marcy go ahead and launch that.
Sure thing. The new equations for fastener head pull-through are based on which of the following? Fastener head diameter, specific gravity of side member, net side member thickness, or all of the above. And 87% say all of the above, 10% a fastener head diameter, and that is it. So which one is it?
All right, it is all of the above. So that looks like the majority of you got that, so that's great. All right, now let's jump into our last chapter here. This is chapter 16, and this is the fire design of wood members chapter. So I mentioned that the changes in chapter 16 were not meant to be technical in nature. They were meant to try to clarify some things and kind of clean up some terminology that was, what had kind of proven to be a little bit unclear. So you'll see some revisions in the terminology to clarify the difference between char depth, which is the A sub char value, and effective char depth. You'll also see this B sub T that we talked about earlier. That's a new name for that specific variable. But so this table 16.21a is where we see the kind of the difference between char depth and effective char depth displayed. And the effective char depth is what we would use in our structural fire design. And what we see here actually is taking into account the fact that beyond that char front, there is wood that has been heated. Even though it has not burned yet, it still has been heated. And as a result of that heating, there is a loss of strength and stiffness, resulting from these elevated temperatures. So we use the effective char depth to do our structural fire design and calculations for things like that. Section 16.3 is the wood connection section, and this was revised to more precisely describe the requirements for protection of the connection from fire exposure. So we clarified that a wood connection, we don't just mean the connector or the fastener, we also mean the portion of the wood member that is included in that connection design. So the wood that is present that connector, kind of for lack of a better word, that connector needs to bite into to form a connection. That needs to be protected as well. The protection can come from wood, it can come from fire-rated gypsum board, it can come from other approved materials, it can be a combination of any of the above. But we did want to clarify that a wood connection isn't just the connectors, it's the wood in the connection as well. All right, so those are the changes in the main body of the document. So Appendix L, I mentioned, was the only appendix that we had any changes in of the appendices. So you'll see the addition of head diameter here in table L3 to facilitate those head pull-through calculations. We also have this new table L6, which is our roof sheathing ring shank nail table. So I said the names again, you know, they're just a dash number and 01, 2, 3, 4, or 5. Some additional resources that we've got we've got a separate e-course that goes into some of the NDS 2018 NDS changes. A little bit longer, a little bit more in depth than what we covered today. The 2018 wood frame construction manual. We also have a program that deals with the changes related to the updated version of that. As you might guess, the update to the 2016 version of ASCE 7 also had an impact in that document. So if you are interested in checking either of those courses out or any of the dozens of other online offerings we have, our website is right there, awc.org/education/e-courses. So with that, that's all I've got. We're going to jump back to Marcy, I believe, to go through just a few closing slides, and then stay where you are because Michelle and I are going to do some Q&A after Marcy is done.
Okay, thank you, Marcy. And thank you, Lori, for providing the second half of the webinar. And we did have some really good questions that came in. One of them has to do with where can I find information related to mass timber? That is one of the areas in the construction industry where we're seeing a lot of growth, a lot of excitement with using mass timber products and what's going on in the industry, being able to go to 18 stories using mass timber. So if you go to our website, which is shown here, awc.org, and you go over here to quick links, have some very important links, especially related to education events, but more to the point is related to tall mass timber. We have a web page that is dedicated all to the tall wood mass timber efforts, has a lot of helpful information, and one has to do with the 2021 IBC proposal code changes. This is some really good information. This lists the 14 different code changes that were submitted and approved. And then this here is a really good document that was developed by AWC that looks at the different types of construction now in type 4 construction. So type 4 heavy timber, that will remain, no changes to that. But we've expanded on type 4 construction, and we now have a type 4A, type 4B, and type 4C. And it gives all overview of the information required for the different types of construction and what's allowed. Now, in addition to that, we have some e-courses here that are recorded webinars from past events that gives even more information about tall wood and related to the adhesives, the fire testing, the outcomes of the tall wood effort. So a lot of information in the fire tests that were performed, et cetera, et cetera. So a lot of helpful information. We also had, and I'll run this to by Lori. Let me bring this over. So there was a question came in about the impact load, and they were asking about preservative treatment, and I believe that's covered in footnote 2. But Lori, do you want to? They wanted to know if the impact load, which is noted with footnote 2, what happens when you have a preservative treated or fire treated structure?
Yeah, you actually do. It is in the part of footnote 2 that wasn't edited, so that's kind of why I kind of brushed through it. But if you are using treated lumber, so you can see it there, if it's pressure preservative treated or if it's fire retardant treated, you are also going to be limited to that 1.6 load duration factor for your design.
Right. instead of the 2.0. Very good. And that
Yeah.
pressure treated is for waterborne preservatives. Okay. And then can you expand upon again? I think you did touch on this, but what type of species or differentiate with those species that need incising?
Yeah. So we refer to the types of species that need incising as refractory species. And that's your Douglas fir larch, your hem fir, and your spruce pine fir. So if you're using southern yellow pine that's treated, southern pine is nice in that it very readily accepts the treatment chemicals, so you don't have to incise it when you apply treatment to it. So you don't need to, if you have treated southern pine, you don't incise it, so you don't need to apply the incising factor.
Great. Okay, so one other question came up is I mentioned about 6-inch dimension and where is it required in heavy timber construction. And so here, section 602.4.8.2, exterior walls shall be one of the following non-combustible material, not less than 6-inch dimension shown here. So, and it allows the fire retardant treated wood. So that's where that 6-inch dimension. And as I mentioned in the 2015 code, there was a proposal that was a code change proposed to eliminate that 6-inch dimension. It did get approved, but for whatever reason, it didn't make it into the printed copy. Now, if you're interested in having that information to show that it was approved, the code approval number or the code number reference number is G179-15. And you can look that up on the ICC website. Another question came in related to connections, and if you have multiple members in your connections.
Yeah, I can take that one. So it typically when we design a connection, our equations talk about single shear where we're connecting 2 members, or double shear where you might be connecting 3 members. But if you're connecting 4, 5, 6, whatever members, that's covered in NDS 12.3.9. And what that tells you to do, kind of the short version of it is you look at each shear plane. And what a shear plane is where we have 2 members coming together. So where 2 members are touching, that's a shear plane. And we look at each individual shear plane as if it were a single shear connection. And we calculate the lowest value of any of those shear planes, and then we multiply that minimum value by the number of shear planes total.
Great. And I don't recall if you touched upon this, but the difference between analyzing the members in TR12 versus the NDS in gaps, can you touch on that a little bit?
Yeah. I didn't talk about TR12, but Technical Report 12 is one of our publications on the AWC website that you can download for free. It provides an alternative approach to calculating your shear or your lateral capacity of a connection. So the one nice thing about TR12 is if you have members that are not in direct contact, that you can use the provisions in TR12 to accommodate for that gap. In the NDS equations, one of the assumptions is that the members are touching each other, that they're in direct contact. So if you don't have members that are in direct contact, or if you have something in between them, like a piece of foam or something that's a very low capacity, that gives you an alternative option for calculating capacity of a connection. To kind of piggyback on that, I saw we had another connection related question come in related to the tip length of nails. And the question was, does the nail penetration include the tip length? And it does. It just depends on what limit state you're looking at, of how much of the tip you're going to use. So for withdrawal provisions, it would include the whole tip for the nail. If you are doing lateral connection provisions, so when we talk about withdrawal provisions, that's where the load is applied parallel to the dimension of the fastener. So you're going to use the full tip length if it's a withdrawal load. If you are in a shear load, or where the load is applied perpendicular to the length of the fastener, you're only going to use half of the length of the tapered tip. And going back to that technical report 12, TR12, there is a whole boatload of calculus and analysis in technical report 12 that shows that that assumption of just using half the tip length gets you to within 1% of an exact algebraic solution that, you know, assumes a function across the sloping portion of the nail. And as the person who single-handedly performed most of that calculus, I can assure you it's not worth it for you to go through it. So just use the NDS assumption. It is a very valid and has been mathematically proven to be very accurate, and it saves you a lot of time.
See, with all of that effort that you went through, we wouldn't have known that. So that's great.
That's how engineers haze each other. It's with calculus.
Yeah, exactly. So another question is related to snow loads, and when do you use the snow loads? When we're dealing with lateral designs. So in the chapter 16 of the IBC, this is the 2018 IBC, 1605.3, when we're doing load combinations using allowable stress design, which I think most people do design by that. Here it says basic load combinations. And there's an exception when using snow load here in our design. And that is where we have flat roof snow loads of 30 pounds per square foot or less, and roof live loads of 30 pounds per square foot or less, then it need not be combined with seismic loads. And that's just when we're doing our lateral loads on our building for seismic design. Then the snow load is not included. But if you're over 30 pounds per square foot, or the live loads, roof live loads is over 30 pounds per square foot, then it does need to be included. Hopefully that makes sense. And then another question came in regarding the firewalls and the allowing diaphragms to go through in high wind zones. So this provision of allowing the diaphragm to go through is just for seismic design category D, E, and F. And if you're in a high wind zones and you're in those design categories, then the diaphragm can go through. But if you're in lower seismic, then per the letter of the code, it's not allowed to go through. And as I mentioned, there was an effort to allow to have the code changed to include high wind, but currently it's not. Hopefully in the future they'll consider it. Here's a link to the white paper or the seismology opinion. I'll put in the chat to everyone so you can get a copy of it. And perhaps you can submit this and go through an alternate means of methods for allowing the sheathing to go through in your area, even if you're in a low seismic zone, but you're in a high wind zone. Okay, there was a question that came in about ventilation under the balcony, if it's all exposed, and whether or not ventilation is provided. And that section of the code talks about those balconies that are enclosed need to provide ventilation. If it's all open, it has its own natural ventilation provided. So no additional ventilation would be needed. Okay, Lori, did you have any other questions?
I think we got one more good one here, and then maybe we can wrap things up. I had a question came in. Can you use the fastener head pull-through provisions for carriage bolts? While carriage bolts are kind of a weird thing, they are not included when we talk about bolts in the NDS. we talk about bolts manufactured in accordance with, I believe it's ASME B 18.1.2. Don't quote me exactly on that number, but there's an ASME standard for the bolts that are included in the NDS, and carriage bolts are not included in that. That being said, the fastener head pull-through provisions will apply to any round-headed fastener, so they would work for a carriage bolt. However, the NDS tables, the bolt tables, especially for lateral connection capacities, those would not be able to be used with carriage bolts. So you do want to make that distinction. The carriage bolts are different than the bolts that we call out in the NDS.
Right. All right. I think that's it. Do you want to close it out, Lori?
Sure. Thanks everybody for joining us today. We really appreciate you coming, and hopefully we'll see all of you next month when we're back to talk about deck ledger and stair solutions.